So, well, basically, we are going to start, and the first lecture, I mean, I will give you the content. I have uploaded the slides already, so you can check it out there. I'm just basically presenting it. Okay, the first thing is, okay, we'll look at set operators, whatever, so this is going to be about unions, intersections, and all that stuff, so I think you're probably familiar with that. De Morgan's law, which I want to stress also. Then I'm going to consider countability, which is a property that needs to be addressed here, especially when considering continuous time. And after that, we'll look at power sets, which is just simply the set of all subsets of a given set. We're going to look at families, which on the one hand is going to be just a subset of a power set. And then later on, I will consider sigma algebras, which is actually necessary for considering random variables. So that's basically what it is. Okay, we're going to look at some properties like closure under set operators, closure under unions, closure under intersections, countable unions, and all that stuff. It's going to be a little bit technical, but it's worth basically considering it. And then I'm going to talk about, especially within this context, especially about so-called probability measures. First off, I'm going to define what a measure is, addressing certain probabilities, and then we're going to look at probability measures, and that's basically what I plan to do today. So I'm not going to go beyond that, even if it's basically 3 hours. Probably not. Okay, so well, I'm not sure basically how much time we're going to spend on that one, but we're going to see. Okay, so the first part is not going to be difficult, but you will need to understand, especially, let's say, probability measures are going to be important, and I'm going to stress, let's say, sigma algebras, which is actually from the from the technical perspective is going to be important, but the exam will not, the total exam based on sigma algebras. It's not going to be the case. We'll also talk about filtrations a little bit, but not now. So not within this context. I'm not sure if you're familiar with these concepts. Anyway, if not, okay, it's actually time to. All right, now have a look at basically sets, especially certain, probably operators they're all familiar with. I'm going to call basically omega to be the sample space. Usually it contains outcomes of random experiments. Okay, so there is always going to be an underlying random experiment which is necessary to consider, and it has a certain outcomes which are uncertain. Okay, so we call basically an experiment a random experiment if the outcomes are uncertain. And and of course, again, so each time you see omega, it's going to be basically probably so-called sample space, which you need to be declared. Let's say it has the following outcomes. So, for example, you can roll the dice, whatever, 1, 2, 3, 4, 5, and 6. And of course, the subset of basically of omega are going to be events, but not every subset is going to be event. Anyway, so let's say you have a subset of even numbers, and then you have basically another one which is containing the numbers that are not greater than 3. Okay, so these could be possible subsets. And what I'm going to do is, again, so just for you to understand this, 1, 2, 3, 4, 5, and 6 are the elements. Okay, so there is a difference between, and 0 is of course not. So, okay, just for make sure that this is the notation for the element. This is the element sign that I use, and this is basically actually disputing it, right? Okay, I think, okay, so I assume you have probably seen this before. Okay, can you see it properly? All right, okay. Now, what I need to basically consider is the definition of a subset. A set is called a subset of another, okay, so A, if it's cursive, right, see, this is basically the subset, and usually I'm referring to subsets of omega, okay? You can also refer to basically different constellations, but that's just basically what I'm referring to most often. If every element that is in A is also going to be in omega. So the fact that basically X is an element of A implies that X is also an element of omega. Otherwise, it would not be a subset. So anything is basically what is in A is also contained by omega, but not necessarily the other way around. Okay, because then if it was true the other way around, then omega would be also a subset of A. So then each set would be a subset of each other. Okay, that's basically the definition, guys. So again, A is called a subset of omega if an element which is in A is also in omega. Okay, that's basically the formal notation. And two sets are equal if and only if, and that's basic. I mean, the notation is, again, you've seen this before. I assume, okay? That's not the strict subset, by the way. So if it basically A is a strict subset, this is something you can also see, all right? That this means that it cannot be equal, okay? Because just want you to remind you, every set is also a subset of itself. So we have basically that any set, whatever it is going to be also a subset of itself. But if it's not true, so if there is no possibility for them to be equal, then it would be a strict subset. Okay, here it's also a strict subset, but that's not true in general. So this is not basically a way to express it. Okay, so that's a notation for the subset, and then you also have, again, the strict version, which is here. Is that understandable? Okay, so, but I'm going to refer to that, basically to that notation. So there is also the possibility for sets to be equal. Two sets are equal, actually, so that's basically the next statement I'm going to make here. Okay, of course, each of them are going to be subsets of omega. I think this is basically understandable because every element of those is also be contained by omega. That's not a surprise. Okay, so, well, and there is a remark here. So if, again, that's the statement that I'm trying to make. I was editing it basically in the wrong way, so sorry if you're not seeing it. If two sets are equal, if and only if they're a subset of each other. Okay, so let me basically make that statement here so you might be seeing this better. Okay, so that's the case if and only if A is a subset of B and B is a subset of A. All right, I think you also see this. So whenever you try to prove that two sets are equal, that's the most common way to do it. You prove two things. Number one, okay, that A is a subset of B, and number two, you also prove that B is a subset of A. And if that is true, that they're going to be basically equal as well, because that is actually equivalent of them for them to be equal. Does that make sense? Okay, so I think you might have seen this before, but I'm going to use it. So sometimes if I show that two sets are equal, this is the way to do it. Okay, I apologize. Next time I'm going to edit this a little bit better, but this time I failed a little bit. Anyway, so here you see the statement. Okay, all right. Okay, guys, now I think you must have seen this before, right? But I'm not sure. Anyways. Okay, next I'm going to consider complementation. What I'm going to stress here is that complementation is always performed with respect to omega. So that is, you can also call it the universal set or even the universe, okay? So complementation is always performed in this regard with respect to omega. The complements are denoted, and there is two different ways to denote this. One, basically, this is the complement of A. That contains everything which is not in A, right? But it must be basically also an element of omega. So that's something which is need to be stressed here. Okay, so those are, among others, 1, 3, and 5, which are the odd numbers. So if basically A covers the numbers that are even, then the complement is containing those which are not. Okay, but it needs to be stressed here that complementation is performed with respect to omega. So although basically 0 is not an element of the set A, which is true, it does not necessarily imply that it is an element of the complement of A, which can be also denoted by A bar, by the way. So this is a more common notation that I use. Okay, so with a little c here as an exponent. This is not an exponentiation, by the way. So this denotes the complement of a set, not the actually some sort of exponentiation that doesn't exist in general. Okay, so I'm going to use that notation preferably, but you can also use the other one. So I'm going to understand if this is basically what you are referring to. I don't know which one you've seen more often, but again, I tend to use the latter just for you. Okay, so just for you to mention that before. Okay, so in the slides during this, basically in the presentation, I'm going to use it. Now, if A is a subset of omega, which it must be the case, right, then the complement must be also a subset. So it cannot be anything outside basically it, okay, because again, this is universal in that regard. This indicates that complementation must be performed with respect to omega. So I just mentioned before, it again, so anything which is not in the in A must be in the complement of A, but only with respect to omega, of course. So that's something which is worth considering, okay? That's something which I wanted to stress here. I'm sure basically you understand it. So if it's not in omega, it cannot be in its complement either. Okay, that's what I wanted to stress. All right, guys, so keep that in mind when you're do complementations. The next remark is going to be, I think, is something which you are familiar with. Yeah, you got a question.
Can we just generalize and call omega a random variable?
No, it's not a random variable. This is just, again, a set containing all outcomes of a random experiment. It doesn't even link to a random variable yet. I'm going to link it to a random variable next week. So next week we're going to define random variables properly. What is actually a random variable? Okay, so you will need to have basically a proper definition for that. But this is we're not there yet, not even close. So it takes, let's say, a few hours to get there. Okay, so I want to come back to your question later on. But it will be attached to a random variable. Okay, some way or the other. Anyways, okay, now the basic rules that you need to be familiar with, among them is, you got a question? You raise your hand, sorry. Okay, is among others De Morgan's laws. There is two of them, and the first one states that the complement of a union is going to be the intersection of the complements. That's what you're going to see. So the complement of a union, let's say two, and that is also even true for more sets. So if you take the union of more than just two, this is going to be fine. The complement of a union is going to be equal to the intersection of the complements of each. Okay, so the intersection of A and, the intersection of the complement of A and the complement of B respectively. That's statement number one. Okay, so if you want to get rid of basically the complement, you can. So you might be breaking into, but you just, eliminate this by using the intersection instead. Okay, so that's something which, that's the first rule. And you can confirm this easily. Okay, so usually actually I prove it, but at this time it's not going to be necessary. And the second rule is basically some sort of the opposite. The complement of the intersection is going to be the union of the complements. Whether you have two or more, it doesn't really matter. Okay, so the complement of the intersection, let's say you have two sets here. Okay, we're going to look at pairwise intersections, if you say. The complement of that is going to be equal to the union of the complements. Okay, so the complement of A and the complement of B, respectively. So these are the two rules. I'm going to apply them here and there. It has certain implications regarding closure under complementation and under unions, but I'm going to come back to that later on. So I'm going to show you that, okay, using the De Morgan's rules. For example, establishing certain properties that families of sets are going to have, but that's okay, so this is just a side note here. So I want you to remember this. Again, I repeat, the complement of a union is going to be the intersection of the complements. That's rule number one. And rule number two, the complement of the intersection of, let's say, two or more sets even, is going to be the union of their respective complements. So that's basically what it would be, okay? I think you have seen this before. I'm not sure, but again, I need to start somewhere. So yeah, this is where I'm going to start. Let's say, okay, I'm going to consider the examples. This is not proving it, but let's say confirming it a little bit more intuitively. So I'm going to take the same example again, which I have taken before. Okay, here is basically, or here are the subsets. And I'm going to look at basically the complements. Now the complements, which I have already addressed, sorry, okay, something is wrong here. These are the complements respectively. And again, so I've done this before, so I'm not going to do it again. And I'm going to confirm De Morgan's law that they might be true. Okay, so again, this is not proving them, but basically illustrating them from intuition. Let's have a look at the complement of the union. Now, what is the union? The union is basically created if you throw everything together. Okay, so you have the union of A and the union of B. If you throw them everything together, it's basically contain every element which is an A or B. So that's what I want to stress here. Not A and B, because that's going to be the intersection. Okay, A or B. That's the logical disjunction, if you basically want to relate to that. Okay, and that's and basically this contains every single element from omega except 5. So that's going to be the complement of that, basically. So that's going to be the complement of the union. All right, I think this is understandable. And what is basically the intersection of the complements? Now you got the complements over here. Okay, so these are the respective complements. You might see this better, so I'm going to stick to that. Okay, the complement of A is here, the complement of B is here. This is the only common element, by the way. All right, so that's going to be equal. All right, this does not prove that basically De Morgan's law are true, but that might indicate at least that this is true. Okay, I don't think this is going to be intellectually challenging when you look at that. So again, this is the complement of A. this is the complement of B. I'm going to be a little bit more actually focused here. And then this is basically, yeah, the same as you saw. So the complement of the union is going to be the intersection of the complements, okay? At least in this case. And that is also true in general. So not just here, but in general. I think you've seen this also, right? So you must have seen that before, I assume. If not, okay, I mean, it's not it's not a big issue, but yeah, you should have seen at least that. And that is also true for the second part. I'm going to look at the complement of the intersection. Now, the intersection of the two, again, what is the intersection of the two? You must find the common elements, right? And that's basically consists of the set containing 2 as its element. So that's A, this is B, right? And then you look for the common elements, and there is only one, which is actually 2. And then you would need to take the complement of that. So everything except 2, but which must be at the same time. It must be actually in omega as well, is going to be actually 1, 2, sorry, 1, except that. So 1, 3, 4, 5, and 6. All right, so that's basically it. Okay, so that's the complement of the intersection of A and B. And that is going to be equal to the union of the complements. Okay, so when you take the complements, they are here, and throw them together, because that's basically what the union operator does, then what you're going to end up with is the same thing. So that's going to be the same as the complement of the intersection. This is actually worth mentioning. So again, I want to basically stress that this does not prove that this is true. However, it might indicate that might be true. Okay, so that is actually confirming, at least for this example, the second rule. And the first one was that the complement of the union is equal to the intersection of the complements. Is that all right? Okay. Okay, so I think, and that is also true actually for more sets. So when you take basically a union of more than 2 sets, how much more? We'll see. Okay, now the next topic is going to be countability. Countability is also an abstract concept. It doesn't necessarily mean that you can count how many elements it has. It simply means that there is a possibility to express the elements of a set in terms of a sequence. That's basically it. Okay, so I'm going to make it a little bit easier. I don't want to talk about bijective functions and all that stuff, because this is actually more technical, even more technical than I do. A set is called countable if actually there's a one-to-one relationship between the number, basically the set, and to that of the natural numbers. But that is a little bit more technical, so I'm going to say a set is called countable if there is a possibility to express it in terms of a sequence, where the sequence must contain actually all elements from the set. This is just a simple definition, but it works. Okay, so, and if that's not true, then it's not going to be countable otherwise, or you can also say uncountably infinite. Okay, that's basically the term. But if it's countable, then you can also say countably infinite, especially if the number of elements is not finite. So this addresses basically to distinguish between sets where the number of elements is not finite. Okay, either it's countable or not. If it's finite, or the number of elements is finite, then it's always going to be countable, because then a sequence, or every permutation even, is going to be capturing every single element that the set has. The question is, what happens if it's not the case? So if the number of elements is not finite, well, then you need to distinguish between 2 different sets or 2 different types. Either it's going to be countable or / countably infinite, okay? Or it's going to be uncountable. These are the 2 categories in general. I'm going to basically create examples so you understand the concept of countability. One of the sets that are going to be countable is the set of natural numbers. Okay, the set of natural numbers sometimes includes 0, sometimes it doesn't, depending on the context. Again, it doesn't really matter whether you include 0 or not. Most of the time, I will, okay? But again, so when I talk about discrete time, I will basically assign a certain value, which to be the starting value. So this is going to be the starting value at the initial point of time. But again, it doesn't really matter whether you basically include 0 or not into the consideration. It's just a matter of definition. 0, 1, 2, 3, 4, and so on. Okay, so as you see, the number of elements that it has is not finite. That is true. But it can be countable, because all these elements can be represented by a sequence. So the first member of the sequence would be actually, let's say, I mean, when you write down the members explicitly, you don't need to. But when you write them down, you can. The first member would be 0, the second member would be 1, the third member would be 2, and so on. So as a sequence progresses, the nth member would be, of course, n minus 1, but that's just, you know, a side note. You would not need to be that explicit. But again, there is actually a one-to-one correspondence to it, so you can see that basically the set is not finite, but is going to be countable, because there is a possibility to express the members of this, the elements of the sequence in terms, the elements of the set, which is supposedly be countable in terms of a sequence where every single element of the sequence is listed. Okay, using the term countable or countability is going to allow me to distinguish between discrete processes or discrete random variables and continuous ones, among others. That's not the only basically categorization, but actually a random variable will be called discrete if its set of its realizations, which it contains realizations or possible outcomes, is going to be countable. This is what the basic definition of a discrete random variable will be. So I'm going to pick that up later on. Okay, it's not necessarily finite. So think about it. Okay, when you run basically probability distributions, the set of the realizations of random variables is not necessarily finite. Even basically it is discrete. There is lots of examples included in here, but I'm not going to consider that one. And of course, a set of all integers, which also captures the corresponding negatives, right? So you have 0, 1, minus 1, and so on. So you can basically rearrange that sequence. In here, in this case, again, I'm not addressing basically how to express it in the general terms, but that's something which is not necessary. You can clearly see that the elements can be expressed in terms of a sequence. So since that's the case, the set of all integers, including the negatives, right, is also going to be countable. It's not finite, but it's going to be countable because there is a possibility to write them down in terms of a sequence. Okay, and that's basically pretty much it. All right, does that make sense? Yes.
Is a countable set automatically discrete?
The set is not called discrete. The set is called countable. The corresponding random variable that takes the values from that set is going to be called discrete, but the answer is yes. So you could call it discrete if you like. Okay, so if these are realizations of a random variable and the set of its realizations is countable, then you can also call the set discrete if you like. But I haven't seen this before, but why not? Okay, so, but I'm calling the random variable to be discrete other than the set of its realizations. We say the set of realization is going to be countable. Not necessarily finite, as you see. Okay, so yeah, there is basic intuition for that, but why not? Okay, so I would not basically complain if you call basically the set of realizations discrete. Okay, why not, actually? All right, now what people or most people don't know is that the set of rational numbers is also going to be countable. And I'm going to show you a way how to express members or elements of the set of rational numbers in terms of a sequence. This is a little bit more sophisticated, but it can be done. You don't need to, okay? So that's not going to be an issue for the exam, all right? So this is not something you will need to establish. But that's very interesting because most people think that if, let's say, a random variable takes values that are rational, that the random variable is necessarily continuous. That's not true at all, okay? So that's basically the other way around. It's going to be a discrete one, okay? Even though it might be, let's say, looking like as if it would be a continuous one. But anyway, so I'm going to define a set of rational numbers, denoting them by Q. Rational numbers are numbers that can be expressed in terms of fractions of two, let's say, integers. Okay, so positive or negative, it doesn't really matter. So I'm going to give you the indirect definition. Of course, it's not going to be relevant for the exam, so you don't need to take notes about that. Okay, so let's say I'm going to call the numerator P and I'm going to call the denominator Q. And that is a set containing basically every fraction there is, where actually P and Q are integers. All right, so that's something which is worth mentioning. They can be both positive and negative, but the denominator cannot be 0, of course, because there is no such thing as dividing it by 0. All right? Now, anything that can be expressed in terms of a sequence, in terms of a fraction, is going to be automatically a rational number. So, for example, every integer itself is going to be rational, right? Because you can also express that in terms of a fraction, let's say, whatever, 200 by 20 or so, which is also a fraction, right? I'm not saying that the representation is unique, but it doesn't have to be. So anything basically which is an integer is also going to be a rational number. Whereas, for example, every fraction, of course, of 2 integers is going to be also a rational number. But, for example, the square root of 2 is not. So you might be basically familiar with that concept, right? When you remember back in school. Or the number pi is not rational, if I recall it correctly, right? Or let's say all this number is not rational either. So again, there is a lot of examples, or the logarithm of 2 basically with respect to base e. But again, there is multiple examples where there is no possibility to express those in terms of a fraction of 2 integers. Now, okay, so the question is, how would you show that it is going to be a countable set? You don't need to. So that's not going to be relevant for the exam. You will need to basically memorize that, okay? But I'm going to show you how to. So again, you can do that by using a matrix, which has infinitely many rows, infinitely many columns. In the first row, you find basically the positive integers. It's actually sufficient to consider only the positives only, because as soon as you got one member which is positive, you can also get the other which is negative. So the next one will be just a negative one, right? Okay. So the first row of this matrix, which is infinitely many rows, infinitely many columns, contains the positive integers and including 0, so the non-negative ones. And the second one is containing basically those fractions where the denominator is equal to 2. So actually, basically, the first row contains all fractions where the denominator is equal to 1. Okay, let me use a different color, so for editing you might not see this properly. So 1 by 1 is of course 1. 2 by 1 is 2 by 1 is going to be also 1. So here in the first row, the denominators are 1. In the second row, the denominators are 2. And the third row, guess what? The denominators are going to be 3, and so on and so on. So you basically see what the structure of this matrix will be. Again, it has infinitely many rows and infinitely many columns. And that's basically because the number of rational numbers, or the set of rational numbers, let's say, is not finite. All right? So again, it basically continues down there. Now, how would you establish a sequence? That's relatively easy to do. Again, you don't need to do it. The first member is going to be 0. So this is basically what I'm starting with. Okay, so let's start from here. And the second member is going to be 1. Okay, and then of course the third member is going to be negative 1. So as soon as you got one member which is positive, you automatically can basically address the next one, which would be negative. Okay, so the third member would be negative 1. Okay, so this is basically how I progress. All right, then I'll go on, and then I consider basically the fourth member, which is going to be 2, you see? And then the fifth one is going to be negative 2. So again, as soon as I hit one member using this matrix, you can automatically basically hit the next one, which is going to be the negative version of it, right? So it's going to be its negative counterpart, because again, the set of rational numbers includes both positive negatives and zeros as well. Okay, now this is going to be the as I progress. Okay, so that's going to be the sixth member of the sequence, 1/2, as you see. So that's basically the sixth member. And then of course the seventh member is going to be its negative part. Okay, here is the wrong index as I recall. Okay, so that's going to be member number 7, which is going to be its negative counterpart. I apologize, we'll fix that one if the slide is wrong, which again I presume it is true. So again, you would just need to move on, and the question is, how would you progress? And then you progress as a snake. I'm going to show you. So then it comes 1/3, then you go back. You could skip that one because 2 by 2 has been already mentioned, so you could skip it, okay, which you would actually. So that's already basically then. And then you go up, right? So then you progress, and this is basically describing how the sequence progresses as it progresses, right? And after a while, sooner or later, you're going to cover every single rational number there is, because that matrix, which is not finite, of course, includes at least all rational numbers that are at least positive. Okay, so this is basically how you move along. You understand this? And then this creates a sequence, and thus the set of rational numbers is going to be, as you see, right, is going to be countable. Okay, I stopped here, right, but you would go on, right? So you would basically continue, right, and then going back and so on. Does that make sense to you? Okay, so this illustrates actually how a sequence of rational numbers can be generated that captures every single rational number there is. Okay, again, this is, the index is 7, that's wrong, but everything else is assumed to be correct. Is this understandable? So this illustrates why the set of rational numbers is going to be countable, although it appears to be not the case. Okay, because members can be arbitrarily close to each other, right? Okay, so again, but still, right, that's not the case. It's still going to be countable. So there is basically elements that are missing, right? Anyways, but sets that are not countable and include, for example, the set of real numbers. It can be shown that it is not the case. And now I didn't consider that one. If you want to check out the proof for that, you can. Okay, so you might Google it or whatever. So there is actually general proof where it demonstrates that however you try to set up a sequence, there is always going to be numbers that are missing from that sequence. So there is no possibility to basically to set up a sequence that captures every single real number that is. I'm not going to find it basically what the real number is. This includes basically, you know, convergence theorems, but I think you understand the point. Real numbers can be thought of as a union of rational numbers and the so-called irrational ones, okay? Which, for example, include the square root of 2 and so on. Now, there is a possibility to show that, for example, R, which denotes the set of real numbers, is not a countable set, okay? So because it has, let's say, more elements, okay? You can basically say that one, although basically countable sets have, in general, infinitely many as well. The set of real numbers has more. So however you try to set up a sequence of real numbers, there is always, it can be shown, and this is basically based on Cantor's diagonal argument, there is always going to be one, not just one, but multiples, of course, that are missing, okay? And it can be also shown that there are actually more missing than which are not, okay? But that's just another story. I'm not going to talk about that. Irrational numbers are basically, you can call it the difference. You will consider the set of real numbers, taking out basically the set of rational numbers, yielding the irrational ones, which cannot be expressed by a sequence. Okay, so that's also a set which is not countable. Okay, so the set of real numbers is not countable, and a set of irrational numbers are not countable either. Okay, which indicates that there are more numbers which are irrational than there are rational ones, okay? Because the numbers that which are countable, their cardinality, this is basically the word, is going to be equal to that of the set of natural numbers, or even less. But anyways, okay, so I'm not going to basically look into that because, again, this is the beyond of the scope of this course. But you should basically know that this is actually the case, and that is also true for every interval there is where the set of real numbers are involved. Okay, so both are not countable. This includes examples. Okay, and again, I'm not going to demonstrate why, but you can check it out. But because the reason is because this is going to go beyond the scope of this course. But there are more irrational numbers than are rational ones, which I mentioned before. Okay, all right. Yes. Again, countable means that, the proper definition would be that there is a so-called bijection between the set and the set of natural numbers. I don't know if you heard the term bijection. Bijection is basically, a function is called bijective if it's injective and surjective, but again, this is too technical. This results actually in the case that you can write them down as a sequence. So basically a set is called countable if and only if there is a bijection to it between and at least one function which is bijective to it and a set of natural numbers. That's number one. And this implies, or this is equivalent to, let's say, that to the possibility that the members or the elements of the sequence, or the elements of the set, sorry, can be written in terms of a sequence. Okay? Because a sequence is actually, I mean, when you look at that, so however you're basically defining it, is always going to be a function that maps, I mean, it's a, let's say, real valued sequence or so, that maps actually real numbers to natural numbers, actually, right? Okay, so that's basically what it would be, and therefore it's enough to basically to consider that one. So I don't need to define bijections by defining countability, but that would be the proper term. So if you Google it, that would be basically the basic definition, but I think it's more intuitive. Okay, so whenever the opportunity comes up that you are able to write the elements of the set in terms of a sequence, then the set is going to be countable. And if it's not true, okay, if this is not true, so again, as expressed, for example, Cantor's diagonal argument, if this is not true, then a set is called uncountable. Simple as. Okay, so either it can be, there is just basically two options, either it's countable or not. Okay, if it's finite, it's always going to be countable. But if it's not, in terms of basically the number of elements, if the number of elements is finite, then it's always going to be countable. Okay, the question is only basically what happens if this is not the case. Okay, all right, yeah, okay, so that's basically it. Now again, I'm going to look at some examples. Open closed intervals are not countable. Okay, so again, technically speaking, it's not very easy to define what an open interval is, or basically what an open set is. I'm not going to, so I'm not going to be strict on that one, but these things will not be countable either. So whenever basically this comes up, let's say, okay, this is the interval containing basically all real numbers between A and B, including the endpoints. So including the lower as well as the upper endpoints. This is actually technically a so-called closed interval, but I'm not going to define that one. Okay, so again, this is this is the set containing all numbers there are between A and B, and including the endpoints. Okay, so that's something which I want to stress here. Okay, so that's a closed interval from A to B. Okay, and that is not going to be countable either. So this means there are more real numbers between 0 and 1 than between, let's say, more rational between 0 and 1, or the total number of rational numbers, basically. That's not a countable set either, okay? And that is also true if you take out the endpoints. If you take out the endpoints, technically you end up with an open interval, so-called open interval. But again, I don't have time to define basically open sets and closed sets, but an open set is going to be, I mean, in this case, an open interval from A to B is going to be containing all numbers that are between A and B, but excluding the endpoints, okay? And that's not going to be countable either. So, and that is also true if you have already a set and which is already not countable, and you take out basically a countable set, which could be basically, I mean, this is actually clear, right? So you have, I mean, the open version is the closed version, right? Excluding, taking out basically the endpoints, right? This set is a countable set, right? If you take out basically a countable set from a set which is not countable, then you end up basically with a set which is still not going to be countable, okay? That is also basically a statement that is true. But anyway, okay, so this is basically how this works. The set of real numbers between minus infinity and let's say an upper endpoint, which contains all numbers that are not greater than that, okay, including the upper endpoint as well, is also not going to be countable. So these sets, among others, and if you take out basically the upper endpoint, that's not going to change anything. So in terms of countability, or let's say the lack of it, it's not going to change. All right, that's something you should know. So these kind of intervals are not going to be countable as well when established on the set of real numbers. Okay, that's basically what I wanted to stress here. Okay, I think, yeah, all right. So, and basically, again, I will come back to this when I'm trying to address discrete and continuous random variables. That's important to distinguish between discrete time stochastic processes and continuous time stochastic processes as well. Okay, so that has something to do with the countability, basically, of sets. Again, I'm coming back to it, but that's not going to be your major focus. Okay, so these are things that I need. Now, the Morgan's laws also apply on so-called countable unions, not just on basically on finite unions that you saw. So if you take basically two sets and you create a union of the two, that's called a finite union. Okay, even if it's basically 3, 4, 5 or so, it doesn't really matter. But you can take infinitely many. That is actually also true. This is a little bit more difficult to show, by the way. So the statement, again, the first statement was the complement of a union is equal to the intersection of the complements. That's still true. But this can be generalized, and this is probably something that you haven't heard of. This can be generalized to countable versions, or to basically to countable unions as well. So when I look at basically a countable union, what is a countable union? That's going to be the total union of countably many sets. And then you would need to address the limit of that. So I'm going to basically do that one. So this is going to be, I mean, there is a union operator, which is also can be used as a sum operator, right? So I'm going to look at the complement of a total union of countably many sets. How do I know basically that I have countably many sets? Because these sets can be expressed as a sequence. So then you can say that the sets are countable, right? So you have actually countably many sets. And I'm addressing the complement of the limit of their total union. And De Morgan basically also generalized that this is going to be equal to the, and again, it says what it says, this is going to be equal to the intersection of the corresponding complements. And since I have countably many, so this is how you say it, I have countably many sets, the intersection of the complements will be the limit of the intersection of basically of the complements. So that's basically what it is. That's the first version, okay? This version is not implied by the regular one, okay? But that is a generalization of the Morgan's laws for countably many sets, okay? Because that's not going to be true, necessarily true, basically. I'm just going to show you examples why, okay? But that's not going to be necessarily true if it's just basically the final union or the final intersection of the complements, whatever, okay? However, if this is true, then it's also going to be the opposite. So this is a generalization. And this generalization also works in both ways. The first rule was that the complement of a union is equal to the intersection of the complements, and that is also applied when you take basically the union of countably many sets, okay, which is here, and that is basically the limit of them. And then that is also true for the second version. The second law would say that the complement of the intersection is equal to the union of the complements of the respective ones. That was it. Okay, so that's what basically what we had seen, right? And now I'm going to generalize that basically for countably many sets. Basically the complement of a limit of a countable intersection. So you have basically the limit of that, basically, or the limit of the base, or the complement of the limit is going to be equal to the limit of the countable union of the complements, and you can see that basically the union for that. So you can see basically here, this works in both ways. This is the complement of the limit of the intersection of these countably many sets is going to be equal to, this is basically how I express it, the union or the limit of the union, basically. So that's going to be the limit of the union, right, of the complements. This is a generalization, all right? Okay, and that is still true, by the way, but that's much difficult to show. Yes?
What is the omega in this case?
Omega is basically the superset that contains all of these. So these sets, A1, A2, and so on, are going to be actually subsets of omega. Okay, but in this case you have countably many. That's the difference. Okay, of course the sample space is of different structure, because if the sample space has finitely many elements, then you could not generate basically infinitely many subsets from it. Okay, that's not true. But again, in general, the number of elements, let's say, expressing like this, is not going to be finite. So if it's finite, who cares, right? You would not need to take those limits. But most of the time, it's not, even if the random variable is discrete. Okay? Yeah, all right, so this is a generalization. Now, okay, don't be scared, but that's actually the same thing. Okay, so similarly, I mean, it's not the same thing, but similarly, it's a stronger statement, by the way. Okay, but it's still true and a little bit more difficult to prove. Anyway, I'm going to look at some issues related to that later on. So I'm going to calculate the limit of unions and the limit of intersections if you haven't seen this before. Okay, so showing you basically some examples later on. Now I'm going to consider power sets in families, and we take a break after that. Okay, I suggest. So power sets or power set of omega most of the time is going to be a set that involves of all subsets. So when you look at basically, I'm going to use that one. This is a smaller sample space, okay, than the previous one because its power set is a little bit smaller than that. Okay, then of the other. The power set of most of the time omega, so I'm going to make a reference to that, is containing the set of all subsets of omega. So you need to collect all subsets that omega has and put them into a set, and that's going to be the so-called power set. The power set is denoted by P, okay? That's not going to be the probability, so this is, let's say, the written version. If you want to take notes, you can, but you would maybe suggest, you know, something like this. So again, I was not very good at that, but you can use that one, okay? So this is actually the notation for the power set. Potenzmenge, that's a German term. I heard the term Potenzmenge, okay? That's a power set. The power set is again containing all subsets as elements. So the set of all subsets, it says for itself, set of all subsets, right? So in this case, it's easy. The power set is going to be finite as well. And here you see the empty set, which is actually the subset of every set by definition, although it might be appearing contrary, but that's also going to be an element. Now you also include these elementary sets. These are going to be an elementary set. The elementary set are sets that have only one elements, respectively. So those are the three. And then you have the doubles, right? So you have basically the set containing 2 and 4, which is also a subset of omega, the set containing 2 and 6, and the set containing 4 and 6. These are subsets of omega, right? And omega itself. So again, every set is a subset of itself. It's not a strict subset, so I'm not talking about the strict one. I'm talking about actually the ordinary one. So that's it. Now, this is basically the power set here. Okay, the power set is of course much larger if the number of elements here of that omega has is greater than 3. So that's why I was basically focusing on that one. Okay, now I want to know basically, I want to address this. So if the number of elements, this is basically, you can call it the norm, let's say. If the number of elements that a set has is n, and n is finite without loss of generality, then the number of elements that the power set has is going to be 2 to the power of basically the number of elements that actually the original set has. So the statement that I'm trying to make here is this: the number of elements that the power set of omega would have is 2 to the number of power of the number of elements that omega has. Okay, so if basically omega has, and you can see this for yourself, 3 elements, then its power set is going to have 8, because as you see, and that's also true, right? So that's a general expression, right? So you can basically see that one. So 2 to the power of 3 is going to be 8, of course, right? You can see in this case. Does that make sense? All right, now that is also true even. So that goes rapidly, right? So if I have 6 elements, it's going to be very big after all. You can also generalize that for countably many elements, but I'm not going to. Okay, so these are so-called cardinal numbers, but I'm not going to refer to them. This is something you will not need. And now I'm going to address a family of sets, and especially actually over omega in this case. So I'm going to call them a family, is going to be a subset of the power set. That's going to be called a family, all right? So again, the power set contains every subset that omega has, whereas a family is going to be a subset of a power set. It can be also the power set itself. So the power set itself is going to be a family after all, right? Okay, for example, that one. Okay, so I'm taking just those, the first three, nothing else. That's a subset of a power set, and that is going to be a family over omega. This is how you say it. You can also say family of omega, but that's not very common. Okay, you understand this? Okay, so that is going to be just a subset. Now here, of course, you can see that that is true, right? So that's basically without any doubt. Okay, of course, the power set is also family itself, right? That's basically worth mentioning. And yeah, so I'm going to show you here that one. Okay, so family over omega is just simply a subset of the power set, which it's clear is. Okay, you see this? All right, so it's not difficult. Yes?
So the family has to have like at least two subsets?
No, not really.
Or also have one?
Yeah, why not? I mean, actually, you would ask, I mean, basically in practice, you would add the term a non-empty family, right? So at least that one element should be there. But actually, I mean, I'm going to talk about specific families, so they will have all at least two. I'm going to tell basically later on what two these are, but not now. It's basically just enough, if you consider that to be just a subset of the power set. Okay? Over omega, technically. So in practice, you could basically make a contradiction based on that, because the empty set is also a subset of every set there is. And how come that basically empty set is both the element and a subset? So there is a quick contradiction that appears, which, again, you're probably making reference to, but that's not the point here. So I'm going to look at more from the practical perspective in this regard. Okay, guys, I suggest taking a break now, and after the break, I'm going to continue. So finish that presentation. How much time you need? 15 minutes, 20 minutes? 15 minutes will be fine. Okay, let's take 15 minutes then. All right. So, okay, is it recording it? It does. Yes. All right. So I'm going to basically do another definition, and this examines specific properties that families can have, among others, closure under, for example, unions or intersections, complementations, whatever. So given a specific set operator, let's say a family is closed under, again, so basically every family there is, I'm going to base the family over omega, of course. And a family should be closed under, let's say, that's going to basically the first one, complementation, all right? So there's going to be multiple ones. If basically every set there is in the family also the family contains the complements of every set there is. So let's say given that the set A is an element of the family, again, the family is a subset of the power set. So think about just a power set there is. Power set is going to be closed under complementation, because if a set contains every subset of a sample space, then you're going to have that basically the complements are also there. So, but anyway, so if a set is there, then this implies or shall imply that the complement must be also there. If there is at least one set for which this is not true, then the set will not be closed. The family, will not be closed under complementation. I hope this is basically explaining it. Okay, so it says for itself. You're going to see later some examples to this. Now you can also define basically closure under unions or pairwise unions. This is going to be start with accordingly. So let's say if two sets are in the family, then let's call them A and B, then their union is also in the family. Okay, if this is not true, then basically the set, this family which I'm talking about, so this is basically what I'm talking about, is not going to be closed under pairwise unions. And that must be true for every set there is. So keep in mind, guys, A and B are arbitrary. So if two arbitrary sets are in the family, and the family is supposed to be closed under pairwise unions, then this must imply that the union, any union basically, must be also an element of the family. So I'm talking about basically the union as a whole. Does that make sense? Okay, now there is also closure under finite unions. Okay, so if basically, let's say a finite number of sets are all elements of the family, then their total union, which is expressed like this, so it's not the limitum, basically, you just simply create a total union, which is, again, if you're not sure regarding this notation, this is just the union of A1, A2, and so on, and AN. So that's a total union, which I refer to it. Must be also an element of the family. Okay, if the family is supposedly be closed under finite unions. And there is a third type, which is, again, addressing the closure under unions. So there was closure under pairwise unions, closure under finite unions, and there is also closure under countable unions. Okay, because the latter, basically this one, is not necessarily true. So if basically countably many sets are all elements of the family, then the limit of their union must be also an element of the family. Okay, so then basically you would consider it the limit as a whole. So keep in mind, this is not an infinite union. This is the limit of the union. Okay, so whenever you see this, again, let me express this a little bit more specific. Okay, sorry, that's not what I wanted to do. Okay, so when you see the union operator, when you see something like this, this is actually addressing the limits. Okay, so this is equal to the limit of their union. Okay, where actually I goes from 1. Okay, so this is basically what you have from 1 to n. Okay, and n tends to infinity. So this is basically what the notation is. So that addresses their limit. Now you probably haven't seen limits of sets maybe, or limits of basically unions of sets. But I'm going to show you one which is more intuitive, so you'll see basically how this is going to work. Anyway, so I'm going to basically create a family of closed intervals and address basically the limit of the union. Okay, so the family of closed intervals can look like this. So let's say you consider a sample space which is supposedly be equal to the set of real numbers. So I'm going to look at a family over the set of real numbers, and specifically addressing actually closed intervals only. I'm going to call them F. Okay, so that's basically what the family would be, and that contains or shall contains closed intervals of the following form. So that's basically a set of all closed intervals, and where the lower endpoint and the upper endpoint have each a specific structure. The lower endpoint shall be, let's say in this case, -1 plus 1 by n. I'm going to create a sequence based on that, but that's just basically what it would be. So take n for basically a specific number. So set, if you're not sure, set n to be equal to, let's say, 2 or something. So you have -1 plus 1/2 as the lower endpoint equals -1/2. So that will be the lower endpoint. And again, the upper endpoint is going to be -1 minus 1 by n, which is going to be -1 minus 1/2 if n is equal to 2. Okay, now n can be anything, and that is basically containing all intervals of this form. I'm going to make 1 or 2 examples, and that shall be a family, of course, because that is a subset of a power set of the set of real numbers, obviously. Okay, so these are the closed intervals, and I'm looking at it right now. That's not the only way, okay, to define it. So that's not a family of the closed intervals. This is just a family of specific closed intervals over the set of real numbers. Now, what I'm going to show you that is, and this is basically interesting in this case, this family is going to be closed under pairwise unions, and is going to be closed under finite unions. Okay, I'm going to show you why. But the family will not be closed under countable unions. So that's a lesson to learn here. I want you to pay attention to this. Okay, so keep in mind, whatever, basically, if you're not understanding this notation, you will, trust me. Again, I'm going to basically collect those. Okay, so this is just a collection of basically specific closed intervals, and I'm going to show you how this is. Okay, so I'm going to look at, for example, following ones. That's going to be the first one. A1 to be defined as where n is equal to 1. So that's going to be for the lower endpoint, -1 plus 1 by 1, which is 0. Okay, and the upper endpoint is going to be 1 minus 1 by 1, which is also going to be 0. So this is the interval from 0 to 0, which is not an interval. but that's basically just a set containing 0 as an element, to be honest. So if the lower endpoint is equal to the upper endpoint, then this is just a set, or this is degenerating to a set basically for this endpoint, which is going to be 0 in both cases. Okay, is that understandable? I mean, there is no such thing as an interval basically from 0 to 0, right? Because the lower endpoint has to be smaller than the upper one. But if it's basically accidentally the case that they are equal, you can define to be a set containing just that number. Okay, that's not an empty set, by the way. Now, as you see, this is an element of the family, right? Okay, you see it? Okay, because n starts at 0.1, right? So that's obvious. So that would be actually an element of the family, of this family, by the way. Now, that is also going to be an element of the family. This is basically the example that I used. The lower endpoint is going to be -1 plus 1/2, which is going to be actually -1/2, and the upper endpoint is going to be 1 minus 1/2, which is going to be 1/2. So this is the interval actually from -1/2 to 1/2, right? Okay, and that's a closed one. You understand this? And that's a real one, okay? And that is also an element of the family, obviously. You understand the point, right? And that's basically, you know, what the structure is. So that's something you should understand by now. If I define that again, so this is, I've already written that down, I forgot. Okay, now I'm going to define another element here, which is A3. That is a set. Okay, so these are, if you ask me what this is, these are, okay, so these A's, A1, A2, and so on, are going to be subsets of omega because these are real intervals, right? Again, as usual. All right, A3, accordingly, is going to be an interval from basically where the lower endpoint is -1 plus 1/3, which is -2/3, and the upper endpoint is going to be 1 minus 1/3, which is positive 2/3, right? So basically calculating that, okay? So you can go further if you like to. So A4, A5, and so on. Now, as you see, okay, so one is always a subset of the next, right? So as basically the sequence, this is basically a sequence of sets right away. So as this sequence progresses, as you see, right? Okay, the intervals are going to get bigger and bigger and bigger. And one is, again, the next one is going to be a superset of the former. Okay, I don't know if you know the term superset. So if A1 is a subset of A2, which is true, then A2 is called a superset of A1. You understand the point? Okay. Now, if you translate the term super, there is no German equivalent to superset, because if you translate that, that's called Supersatz, but that's a different story, right? So when you do weightlifting, that's nothing to do with that, okay? So that's not the Supersatz, but the superset, or Supermenge. I haven't seen that expression before. Anyways, okay? But again, again, so as you see, okay, so the next one is always going to be a superset of the former, right? So if you continue with that, and this is actually called a sequence which is strictly increasing. So whenever you have basically a sequence of sets where actually the next one is always going to be a superset of the former, which it is the case, right? So then you can call the sequence of these sets to be strictly increasing. And if it's the other way around, where the next one is always going to be a subset of the former, which is also be considered, then the sequence, or the sequence of these sets can be called to be strictly decreasing. That's the term. Okay, so here in this case, as you see, okay, so this is also what I've written down here. Okay, so and that's something you should also see. Now, if one set is always a superset of the other, right? Whenever you take two out of them, okay, one is always going to be the superset of the other, namely with the bigger index, of course. So that is also true for basically if you take out, let's say, A2 and A10, right? So the one with the bigger index is going to be a superset of the other, right? Whenever this is the case, what happens if you basically, I mean, two sets, I haven't addressed this before, but let's say if you take the union of A and B, where actually A is a superset of B. Now, if A is a subset of B, where B would be the superset of A, of course, this is going to be B, right? And that is also true here, because that's already there. So if you take everything which is in, let's say, A2 or so, and create a union of A2 with A3, all you find is basically A. So because the intervals are strictly increasing. Okay, so that this is something that you should see here, right? So this is AJ, where basically J is the bigger index here, right? You see? Then this means that whenever you create basically, and when you look at that one, whenever you take out basically two sets of that sequence and create a union of them, you find that this union is always going to be an element of the family also. Okay? So again, if AI and AJ are elements of the family, right, which is basically here, this implies that the union is also an element of family, right? The union is basically going to be the superset, but it doesn't really matter, right? That's also true. So that's basically true across the board. Whenever you take two out, you find that the union is also going to be an element of the family. So this means that the family is going to be closed under pairwise unions. You understand what I'm saying? This is basically clearly demonstrating it. Okay? So even if it's not finite, you see? So you can basically say that the number of elements that the family has is not finite, but that doesn't matter. Okay? Whenever you pick two out and you take a union of that, you'll find that the union is always going to be a member of the family. So the family will be closed under pairwise unions. That's actually true. Okay? So that's basically what you'll have. Now, that's...
would it be the same if it would be slightly decreasing? If it's always closed?
That would be also the case, where basically, because if you take, one would be, actually the next one would be a subset, or strict, let's say even a strict subset of the former, and then when you create a union, then what you would have is basically instead is that whenever you take the union of the two, you're always going to have that one with the smaller index, because the set with the smaller index would be the superset, basically in this case. But it doesn't really matter. So I'm not basically addressing explicitly what the union of the set is. I'm addressing the issue that the family, this family at least, of closed intervals is going to be closed under pairwise unions. Okay, so not because it's closed intervals. So closure under pairwise unions, that's a term. Okay, but that's not the reason why basically the family is closed. Okay, so the fact that I'm basically creating a family of closed intervals has nothing to do with the issue that the family itself is going to be closed under pairwise unions. Okay, so that's the issue. And is also going to be closed under finite unions, not just under pairwise unions, but also under finite unions. When, let's say you got three of them. Okay, so you pick three, whatever that is. Okay, so one with index A, the other with the index J, and then the last one with index K. And let's assume that basically without loss of generality that K is the greatest index there is. Okay, now as you see in this case, since the sequence of these sets is strictly increasing, you find that basically AK is the superset of every other. So when you basically take the union of those, this is what you're going to get. And AK is the member of the family, so is the union of three sets is going to be also there. So that is also going to be closed under finite unions. So whenever you take basically a finite number of sets out of the family and take the union of those sets, you'll find that this union is also going to be a member of the family as well. You find that? Is this understandable now? Okay, and that's basically what it is. Okay, so this is actually demonstrating it more, let's say, a more complex issue. Okay, and that is also going to be closed under finite unions. So not just under pairwise unions, guys, under finite unions as well. There is a possibility to generalize it using complete inductions, by the way. So whenever you use complete induction, you'll find that closure under pairwise unions will be equivalent to closure under finite unions. So whenever a family is closed under pairwise unions, it's also going to be closed under finite unions. But I'm going to summarize these relationships later on. Okay? Now, this is, however, not going to be true if I take closure or examine closure under countable unions, because the limit of those unions will not be in the family. I'm going to show you what the limit of that is. So again, I will basically take the limit of the union of those sets. So again, A1 was defined accordingly. Okay, so AI, just for the record, you're not sure what this is. This is an interval, this is a closed interval, where the lower endpoint is -1 plus 1 by I, and the upper endpoint is going to be 1 minus 1 by I. You understand the point? Okay, so that's basically how it's constructed. Let me stress this a little bit so you see it better. I hope at least. Okay, and this is basically where it is. Now, what I'm going to do is I'm going to calculate the limit of those things. And you need to understand what these are. Okay, so first off, again, maybe what we do now is looking at it, how these things would look on the, let's say, basically on a straight line. So let's say I'm having that one here. Okay, here is 0, here is 1, here is -1, and the first one, which is denoted by A1, right? This is just a single element here, right? I mean, okay, the set containing that single element, which is 0, because the lower endpoint and the upper endpoints are the same. Okay, which is not an interval, technically speaking, but if I declare it to be that one, that this is just a set containing just 0. Okay, you understand this? Now next, I'm going to consider, let's do A2, because that's the next one. We already done that. Okay, so here's a straight line, real numbers. Okay, you got 1, here you got -1, and the lower endpoint, again, these are closed intervals. The lower endpoint, I'm going to use the same color, that was it. The lower endpoint is -1/2. This is here, okay? So in the middle, between -1 and 0, and the upper endpoint was or is +1/2, okay? And everything between. So you have everything between, okay? You see? Now, next, I'm going to look at A3. It might be a little bit easier to see. Whatever that is, again, I would already address it. Okay, so looking at basically the straight line, it will help. Okay, so you got -1 here, and then comes 0, then you have 1. If you take that, -1 plus 1/3 equals -2/3. That's the lower endpoint, and the upper endpoint is 1 minus 1/3, which is +2/3. So this is here, check this out. This is, I mean, again, okay, so -2/3 is here, and that's going to be the close interval here, somewhere. Again, I'm not an artist, but I think you got the point now. Okay, now you can clearly see what happens as the sequence of those sets progresses, because, and that's basically what I'm going to do. Okay, so I mean, let's take another one so then you'll see it better. Okay, A4, which is going to be the next one. This is going to be an interval where the lower endpoint is -1 plus 1, basically 1/4, which is, just a moment. Okay, so here it comes, -3/4, which is, again, so this is half of the half. I mean, that's even closer to here. Again, it doesn't really matter. So -0.75 technically, and that's over here as well. And this is a closed interval too. So the endpoints are included in there. You see? Now, okay, you could probably imagine how this continues if you go on. Because what I'm interested in is the limit of the union of those intervals. Okay? And who can tell me, I mean, maybe you can see this here. I'm not sure whether I'm sufficiently enough to express this, but what do you think what the limit of this union will be? Yes, you got an idea. Yes. But, yes. All right. So how do I express it? So the lower endpoint is going to be -1, and the upper endpoint is going to be 1. That's true. You see? They're getting closer to that, as you see. But do they reach them, those endpoints? No. So that's going to be an open interval coming out here. You see? So the limit of the union of these closed intervals is going to be open now. But the issue is, this is not an element of the family anymore, because the family only contains closed intervals by definition. You understand what I'm saying? All right? So just because, and this is basically illustrating this issue, right? Because whenever the term infinity comes up, there is contradictions involved. And this is basically one example to express it. Okay? So the limit of a union of countably many intervals is not going to be necessarily closed even if the intervals are closed themselves. Do you understand that statement, guys? Okay? So although the family is closed under finite unions, it's not going to be closed under countable unions. Because the limit is not there. You see? It's not in the family. The family only contains closed intervals. It's closed under unions, right? Under pairwise unions and finite unions, but not under countable unions. And that's basically the statement that I'm trying to establish here. I'm not sure whether I succeed or not, but you can decide for yourself and then when you evaluate the course. And all right, so I'm picking those stats again. Okay, so these were the sets that are involved. And as you see, the limit is going to be yielding the open interval, which is not an element of the family. Okay, so though the family is closed under finite unions, it's not going to be closed under countable ones. Because this is an open interval and the family is a family of closed intervals over the set of real numbers. You understand the point? Okay, so there is an issue here. All right, so whenever basically infinity comes up, things are, the statements that you might be thinking they are true, not necessarily true. Okay, and that's basically the example that I wanted to use to establish that. So the family is not going to be closed under countable unions. And this is something that I want to stress, although it is closed under both finite and pairwise unions. Okay, do you understand this, guys? This is very, I mean, again, this is still not the focus when it comes to stochastic processes, but again, I will need to establish the concept of random variables, and I want to do it sufficiently, and I will need to do that. Okay, so you need to have something basically which is actually addressing this issue. All right. Okay. Next, again, this is basically what I'm trying to summarize here. So the previous example is just summarizing these results, and let me try that. Okay. So first thing is closure under pairwise unions and closure under finite unions are equivalent. I said this before and I'll say it again. Okay. And the reason for that is because the set operator union is associative. I'm not sure if you know the term associativity. Okay, so whenever you create a set of, let's say, 3 sets, okay, this can be expressed by the union of 2. So the first one would be basically the union of A and B, and then comes the union with C. All right. So if it's true, if the statement is true for pairwise unions, then it also must be true for a union of 3 sets, right? Due to induction. This is basically why that is also true for when you consider complete induction. Okay, so that's why if a family is closed under pairwise unions, it's also going to be closed under finite unions at the same time. Okay, those things are equivalent. If it's closed under finite unions, it's going to be closed under pairwise unions. That's obvious, but basically due to the associativity of the union, associativity means that you can set, so when the operator comes up, okay, so when you basically take a union of 3 or even more, then you can set parentheses wherever you like to. So you can set, and let me just basically edit this. So this is called associativity here or here, okay? In this case, you got 2 options. Okay, if you got the option to put parentheses wherever you like to, you also have the option to basically to leave them out. That's what associativity is. So the union operator is associative. And here, you got the union of 2 sets. This is the first, and that's the second. And that must be true also for that one. If there is closure under pairwise unions, there is also closure under finite unions. Point blank period. You understand it now? Okay, so that's basically the issue why they are equivalent, by the way. So that can be shown. Okay, so again, the reason is because the union operator is an associative one. Okay, that's the basis basically for that. If that was not the case, then it would not be the case. Okay, and also the intersection, by the way. So the intersection operator is also an associative one. But anyway, closure under pairwise unions, however, is not equivalent or does not imply, and this is basically what you saw just now, does not imply closure under countable unions. Because the open interval was the limit, as you saw, of the union of those closed intervals. and the open interval was not an element of the family. Okay, but that can happen because the limit of closed intervals, I'm not saying it is always open, but it can be open, especially when the sequence of those intervals is strictly increasing. Okay, so again, but it has to be convergent at that time. So it's not just strictly increasing, but it has to be some sort of convergence there as well. Okay, but that's basically what illustrating it here. Does that make sense to you guys? It's true the other way around. So if it's closed under countable unions, that is also closed under finite unions. You can also just break it off, right? Okay, you would not need to take the limit. You could just stop at some point. You would not need to go basically that far. But if you take the limit, it's not necessary there. So as you saw basically in the previous case. However, again, as I mentioned before, if there is closure under countable unions, then there is also closure under finite/pairwise unions because both are equivalent. So that's basically what it is. Okay? And that's basically what I mentioned here. Does that make sense to you? Okay? I hope it does. All right? So it doesn't work both ways. Now, that's basically the term. Now, if it's closed under pairwise unions, then it's, and I mentioned before, a family is also closed under finite unions. I had that already. I just basically restructure it. And what I'm going to do, again, so it's not going to be necessary for countable ones. And now here comes complementation tool. So if a family is both closed under complementation, which means that if a set is there in the family, then this implies that its complement is also there. Okay? That's closure under complementation you saw. Okay? If a family is closed under complementation and pairwise unions, then, and this is basically another implication, the empty set and the sample space are always going to be element of the family. That's one implication. Okay, so this is basically what I'm trying to address here. So whenever a family is basically both closed under pairwise unions and closed under finite unions, this implies that the empty set is an element of the family. It must be the case. So there is no way to get around that. Because again, if you take a set and the intersection, I'm going to prove this, so I will talk about that later on. That's number one. And number two, the sample space must be also an element of the family. Otherwise, it cannot be the case. Okay? So any set that does not, any family that does not contain either the empty set or the family, or actually both, because it must contain both, cannot be either closed under complementation or closed under pairwise unions. I'm going to prove this quick, so let me express this. So let's say A is an element of the family. Again, the purple one is the family, right? So you can distinguish between the two. And this implies that the complement must be also an element of the family, otherwise the set would not be closed under complementation. That's basically one implication here. If it's closed under pairwise unions, then this means that whenever basically a set comes up and then the union of the complement, I mean, the question is, I mean, this thing must be an element of the family. Why? Because the family is closed under pairwise unions. Okay? Now, what do you think what basically comes out if you take the union of any set with its complement? This is going to be the sample space itself. And since the family is closed under pairwise unions, this means that the sample space must be an element of the family. This is just what you're going to see here. Okay, so this implies that since it is closed under pairwise unions, the issue is that the sample space must be an element of the family. Otherwise, it would not work. Okay. So if the sample space itself is not an element of the family, you either have no closure under complementation, or you have no closure under pairwise unions, or you have both. Or neither. Apology. Neither of the two, right? Okay, but at least one of the two would be basically violated. All right, that's one issue. And what is the complement of the sample space, guys? I haven't talked about that, but the complement of the sample space is empty. And since the set is also closed under complementation, this implies that the empty set must be also an element of the family, right? Okay, so that's the other thing. So since the complement of the sample space is empty and the set is closed under complementation, this means that the the family must contain, and that's basically the final result, must contain any family basically that wants to be closed under complementation and pairwise unions must contain both the empty set and the sample space as its elements. Is this understandable? Okay, so that is a statement that I'm trying to make here. That's number one. Okay, so here see that. Okay, now next, if a family is closed under complementation and pairwise unions, then it's also going to be closed under pairwise intersections. And that's something which I'm also going to address. Okay, so pairwise intersections is also going to be there. What does that mean? Closure under pairwise intersections, as it suggests, if two sets are elements respectively of the family, then this means, all right, so again, let me use a different color so you see it better. Then this means that this, again, their intersection as a whole is also going to be an element of the family. Okay, so that's basically what the term would mean. That's closure under pairwise intersections. And the reason is because De Morgan is true. The laws of De Morgan are true. That's the reason. I'm going to show you why. Okay, so again, if two sets are there, then this implies that their intersection is also must be there. And I'm going to show you why this is. So this is the formal statement that I'm trying to make, and I'm going to prove this now. So let's say two sets are basically each are elements of the family. Then this implies that their complements must be also an element of the family, respectively, of course. Okay, because otherwise the set would not be closed under complementation if any of the complements would missing. And then, of course, you also have that the union of the complements is also an element of the family because the set is also closed under pairwise unions. You understand the point now? So that's basically also an issue, right? Okay, now, according to De Morgan, the union of basically of the complements is equal to the complement of the intersection, right? That's the issue, right? So the complement of the intersection of the two must also be an element. And what is the complement of the complement? Because that's something that you also need to address. So what is going to be the complement of the complement, right? Then, of course, this operator complementation is called idempotent because it eliminates itself. So if you take the complement of the complement, that's going to be the set itself. So this implies that the intersection is also an element of the family. Okay, whenever a family is closed under complementation and closed under pairwise unions. Does that make sense? Okay, so this is a statement that I basically just shown here. Okay, according to De Morgan, this is true. Okay, the union of the complements is going to be the complement of the intersection. The set itself is going to be closed under complementation. So the complement of the complement is going to be there, right? And the complement of the complement is actually the original set itself. So this means that the set or the family is also closed under complementation, by the way. So that is also true, okay? So you can see this over here. Okay, so whenever this comes up, this means that their intersection, you can see this here, is also going to be an element of the family, obviously. Okay, so that's something you should understand here. Okay, I hope basically you do. Does that make sense at least? Okay, so this is it, guys. Okay, so whenever this is true, then that is also true. Okay, all right, and these are the basic operators. So you can also express any other operator as well, and that is going to be true as well. Okay, now if it's also going to be closed for the finite version, okay, and that is also because the intersection is associative. So if a family is closed under complementation and pairwise unions, then it's going to be also closed under finite intersections, not just pairwise intersections, because closure under finite intersections and closure under pairwise intersections are equivalent also due to the fact that the operator, intersection operator, is an associative one. And so hence, this is also going to be true if you have basically understand, but not necessarily under countable intersections. Okay, so to achieve that, you need to have closure under countable unions, not just under pairwise unions, but under countable unions. So whenever a family is closed under complementation and countable unions, then it's also going to be closed under countable intersections, okay, but not basically before that, okay, because that's the point. So I mean, of course, closure under differentiation is also what you have, because the difference operator can be expressed in terms of intersections and the complementation. So A without B is going to be A and not B, okay? I hope this is obvious. Okay, so since it's closed under intersections, pairwise intersections at least, and closed under complementation, the family is going to be closed under differentiations as well. Okay, so that is what you will also have, and that's also going to be true. All right? Okay, now a family that is closed, and this is basically what is going to be important, and there is no way to basically to avoid this. A family that is closed under, number one, complementation. Okay, I'm going to basically come back to this statement here. And a family which is also closed under connable unions, again, connable unions, is going to be called a sigma algebra. So a sigma algebra is a family. A family is a subset of the sample space, subset of the power set of the sample space, right? But a specific one, okay, which is, number one, closed under complementation and closed under connable unions. And this is required here, that is closed under connable unions, as you see, because we need to have the limits, for example, of the union of closed intervals to be incorporated as well. Not just basically finite unions, but also the limit of those unions, okay? And that is the issue, okay? So to address basically random variables properly, but I'm going to come back to that later on. So this is what the sigma algebra is. Now, whenever you see the term sigma around, okay, in these names, this is also, you can associate it there with countability, okay? So that's, a simple algebra is just a family that is closed under complementation and closed under finite unions. And if it's called sigma algebra, then it's going to be closed under complementation and closed under connable unions. You raise your hand, so.
Yeah. So could you discuss the example that we have with this union? So the example is not sigma algebra, right?
Yes, that was not one, because it was not closed under connable unions. But if you remove the term sigma, okay, so you define it to be so-called algebra. An algebra is a family, okay, so it's called algebra. This is not part of the script, but an algebra is a family which is closed under complementation and closed under pairwise / finite unions, okay? It must be finite. That's the term, okay? That's so, and whenever sigma comes up, okay, that this is also referring to some countability of some sort, okay? So that's the issue. I don't know why sigma, okay? I don't know, basically, it's not me, so anyways, okay? So there is also going to be sigma additivity, sigma subadditivity, you will see basically later on. Okay, so closure under complementation means that whenever a set is an element of the family, its complement is also going to be an element of the family. That's number one. And number two, and whenever basically connable mini sets are elements of the family, that this means that their respective limit of their corresponding union is also going to be an element of the family. So I'm talking about that one as a whole, okay? So here it is. It doesn't let me do it. Okay, no, because that was white, sorry. So basically the limit of the whole is going to be an element of the family, okay? You understand this? And that was not true, as you basically recognize. That was not true for the family of closed intervals, okay? Now, there's always going to be a practical issue when establishing sigma algebras, because it's a very abstract thing, okay? It's only defined indirectly. So the question is, what is in there? Well, what's not? Sometimes it's not even to basically be able to address. But here in probability theory, if you have a sigma algebra defined, the elements of the sigma algebra, okay, so the sets that are in there, are going to be called events. So that's basically what an event is. Okay, so the elements, this is not part of this slide, but it will be part of further slides, because you might ask yourself, okay, how does that relate to probability calculus? And the answer is because I need to define what an event is, okay, to which basically probabilities can be assigned a certain way. And events are elements of the sigma algebra on a sample space in a sigma algebra on a sample over basically, or you can call it basically a family, but it's called, basically it's called on a sample space. So sigma algebra on a sample space, which is a family over the sample space, is going to be a family which is number one closed under complementation, and number two is going to be closed under countable unions. And why it's necessary closure, I mean, why is it necessary for closure to countable unions is because I want to have the limits too. Okay, so I want to have basically address the limits too. Okay, so not just basically, for example, that a random variable takes values between 1 and 2, okay, which is a closed version, including the lower and the upper endpoints, but also the issue where the random variable takes value between 1 and 2, excluding the endpoints. Okay, I want to have the probability for that as well, not just the probability basically for closed intervals, but also the probabilities for open intervals. Okay, and that's the, I mean, to put it in a nutshell, that's basically what it is for. Okay, now when it comes to applications, it's kind of weird because there is, again, when you read a paper about, you know, financial modeling and all that stuff, and it's always start by sigma algebra, blah, 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 but okay, you read through it, but it's not specified, so nobody knows what it is. But, you know, okay, I'm going to talk about that later on. Okay, so you see this quite often when you read, for example, continuous time finance papers. Okay, so, and you have a sigma algebra there, and the question is what to do with it. And my answer will be not that much. Okay, but I'm going to come back to that later. Okay, so you will not need to take care of that much. Okay, but you need to know what it is. Examples include the following. So for example, the family that contains just a sample space and just the empty set is the smallest sigma algebra there is. Okay, so you cannot go beyond that. That is a sigma algebra. Okay, why? Because it's closed under complementation. So any set which is in there has also its complement in there, and it's closed under pairwise unions, which in this case also implies closure under countable unions, because if the family is finite, okay, if the family is finite, which it is, so or the number of elements, sorry, if the number of elements of the family is finite, which it is, there is just 2, okay, then closure under finite unions will also imply closure under countable unions, but that's an exception, okay, so that is an exception, guys, okay. So that is a sigma algebra. You can easily show that. This is also one. Okay, the power set is, right? But they're not going to be appropriate. So why would just basically not say, okay, I take everything what I have, and the issue is because those sets will not be measurable in general. But I'm going to discuss that later on. But it is a sigma algebra still. It's closed under countable unions. All right, and it's closed under complementation because it contains every goddamn subset that the sample space has. Okay, so there is nothing outside of that. Actually, that's the biggest one. So this is, again, this is the smallest one, and that's the biggest one in general. And you will always, most of the time, you have something between. I'm going to come back to that later on. So for example, that one. This is also a sigma algebra because it's closed under complementation, and it's closed under countable unions even. Okay, again, it's finite, so the number of elements is finite. It has 4 elements. Okay, so there is no way basically to generate infinitely many sets here if it has just finite number of sets. Okay, so this is not very an issue, but again, you'll see that later on. And A can be any subset, by the way. Okay, in this case, but that's going to be actually a family, which is a sigma algebra here. Okay, now those are not the ones which are relevant. I'm going to show you basically, I'm not sure if you have time, probably not, so not this time, but next time, basically that there are also sigma algebras that are going to be different. But anyway, a family of closed intervals that you basically suggested is not a sigma algebra. And among others, because it's not closed under countable unions. It's closed under finite unions, right? But it's not closed under countable unions. And I'll just show you that why this is. Okay, so taking just an example. Okay, so a family of closed intervals over R, which I basically expressed, was not a sigma algebra. Okay, because the limit of their union was not an element of the family, among others.
One question. So
Yes.
basically, if we do not have infinity, most likely we will have signal.
No, because again, we had this family was not finite either. So as far as you remember, it consists of basically a non-finite number of sets. Okay, but still was not enough. Okay, so whether basically the family has finite number of elements or not, this is not determined. Basically, that's not sufficient basically to say whether the family is a sigma algebra or not. Okay. You understand the point now? Okay, so that was basically an example which I've already discussed. I'm not going to discuss it again, but this is something which is you should see. I mean, it's not closed under countable unions, among others. It's not closed under complementation either, but that's just a different story. Okay, but the previous example, and the purpose was the previous example that showing you that just because a set is closed under pairwise unions / finite unions, it's not does necessarily imply that it's also going to be closed under countable ones. Do you understand this, guys? Okay. All right. I'm going to show you later on something issues with the sigma algebras which are going to be important. This is going to be theorem 1.25. I will edit the script so you're going to see this after the lecture. So when you feel like it, you can read it if you want to. The intersection of countably many sigma algebras. So even that is true for a second, is also going to be one. This is proven there, and I'm going to skip it. So whenever basically sigma, I mean, these families come up, and all of them are sigma algebras, you find that the intersection is also going to be one. This can be shown relatively easily, but I'm not going to. So I'm not going to waste your time on that because I'm going to stick to the point. But that's necessary. So if you want to check that out, the proof is going to be there. Okay, you can also take it with you in the exam, but you will not need it. So let me say this, you will not need it. So this means that, let's say, if you have those sigma algebras, if you're not understanding the statement, if let's say A1 is a sigma algebra, A2 is a sigma algebra, and you have a sequence, right, even, which is not finite even, and all of them are, you can define, maybe you can define those, then basically their intersection, or the limit of their intersection, is also going to be one. Okay, so that's basically what the statement is. This is a very important one, by the way. But what I'm going to do is I'm going to show you that it is not necessary to declare the structure of the sigma algebra that you're using explicitly. Okay, that's a very important issue. So although it exists, it's not necessary to specify how it looks like explicitly. Not even implicitly, so not even basically in general terms. And this is done by the next theorem, which is theorem 1.26, interestingly. Okay, so whenever a family comes up, let's say you have a family, which again, so F is not necessarily a sigma algebra, so it could be basically a family of closed intervals on a set of real numbers, for example, which is not, we have seen it. But the issue is it doesn't matter, because there is always going to be a sigma algebra, which we call the smallest sigma algebra, that is generated by the family. Okay, so whenever you basically specify specific sets that are subsets of the sample space, and if you put them together to a family, this whole thing is going to be a family, of course, but not necessarily a sigma algebra. It doesn't matter, because there is always a sigma algebra that contains every single element of the family. So this means that you don't need to prove, or you don't need to specify, sorry. I mean, you would need to show this. It's getting dark, so you probably need some, not sure which works. Probably that one here, okay. It's getting dark, but I'm going to be finishing that one very soon. Okay. So there is absolutely no necessity to declare sigma algebras explicit, neither explicitly nor implicitly, when it's basically specifying them, because there exists, okay, even if just specific members of the families are going to be relevant, okay? So, i.e., the smallest sigma algebra, which is generated by the family, is going to be the sigma algebra that is a subset of any sigma algebra containing the elements of the family, okay? So that is actually the limit of the intersection of all basically that have them. And this is something which always exists, Okay, now I have shown this here. Okay, so you need to understand this. And again, but this theorem claims that if a family is not a sigma algebra, which is typically true, right? So most families are not. Okay, because either they're not closed under complementation, or they're not closed under countable unions, even if they are closed under finite unions, or neither, right? Okay, so most families are not. It doesn't matter. Because this theorem proves the existence, or at least claims the existence, that there is still a sigma algebra that is generated by the family, i.e. the smallest sigma algebra, which is a subset of any sigma algebras that have the elements of the family. And that is going to be 1. So why would you, based on time, basically declaring that? Okay, so that's basically what it would be. Okay, now I'm going to show you that statement still. Okay, so this implies that there is no necessity. This is basically show you that neither to explicitly nor to implicitly, so not even basically implicitly, specify a sigma algebra if just a family is known, because there is always going to be one which generates a sigma algebra. So that's the reason why when you read papers like, you know, related to continuous time finance modeling, and sigma algebras are introduced and filtrations are introduced and all these technical issues are introduced and nobody cares about them. I mean, this theorem gives you justification why you don't need to. Okay, I mean, simply is, because not even basically not even specifying them. They are abstract. Okay, so that's basically also preventing you to actually to specify them. But not just that, theorem allows you to skip them. Okay, so to be honest, I cannot recall any paper related to continuous time finance modeling where I have seen a specific sigma algebra which was given in terms of an equation. Okay, and that has the reason why, basically, which it is. Okay, so if you're not understanding it, it doesn't really matter, because it basically theorem indicates that you will not need to, and that's the statement that is. Okay, which is quite interesting. Okay, so you would not, we know that it exists, but you don't need to take care of them. Okay, and that's pretty much it. Now, let me prove that quick, because that's, again, I'm going to use a previous statement there is. So there exists basically sigma algebras of which the family is a subset of, clearly. For example, the power set, which is always 1. Okay, so the power set is always a superset that contains which has every family as its superset, by the way. There is no exceptions to this. Okay, so number 1, this is basically indicating that there is at least one sigma algebra which has the member of the family. Okay, which could be the superset. So in a worst case scenario, you would take just a superset. And number 2, the statement that I'm going to basically make is that if you collect every single sigma algebra there is containing the family as its elements, okay, it's probably not just the power set, it's going to be also the others. So if you pick those and you take the intersection of those, that is going to be a sigma algebra itself. And that's going to be the smallest one that contains the family, okay, because that is the intersection of those is actually the smallest. Okay, you just need to look at the common elements, and that's it. Okay, and theorem, the previous one, is actually stating just that. So whenever you have sigma algebras containing the elements of the family and you take the intersection of those, you find that the intersection, whether it's countable or not, it doesn't really matter, is also going to be 1. Now this is more interesting to prove that, but okay, I skipped that. So if you want to read it, you can, you will. Okay, so if you want to, you can, but you don't need to. So well, again, I'm not going to basically bother you with that during examination, but you would need to know that these things exist, and yeah, so that's it. So the intersection of those basically must contain the family, and that is supposed to be the smallest one, which there is, and that's basically what it would be. Okay. All right, guys, I'm not sure how tired you are. Let's see basically what comes next. Okay, maybe just an example to this. Okay, the family of intervals, which I wanted to talk about, and just one thing. I'm going to define this case, the Borel sigma algebra. This is a very famous one. Okay, so whenever this comes up, the so-called Borel sets. Okay, that is the last thing that I'm going to consider today. Okay, and then we're done. Okay, you look tired, so I think I don't want to insult you, but that's a fact. So I'm two. Okay. But anyway, okay. So that's the final one. Now, again, I've mentioned before that the family of closed intervals over the set of real numbers, typically if it has this structure. So in the previous case, it was -1 and 1. Here is just A and B, okay? Or -1 plus minus, blah, blah, blah. So this is just all closed intervals there are, okay? Is not going to be a sigma algebra in general. We've seen this before, okay? I took one example and showing you that. That was not, but that doesn't matter, okay? It doesn't matter. So it's not a sigma algebra, we've seen this. But theorem 1.2.6 will allow you to consider a family which is actually, or a sigma algebra which is generated by the family that will contain all closed intervals on R. Simple as. And everything else, which means that it also contains the open intervals, because the open intervals will be actually, or can be expressed in terms of limits of unions of closed intervals. You understand it? Okay? So if a family actually of closed intervals generates a sigma algebra, then this implies that the sigma algebra will also contain the open intervals too. Not just that, but not just the closed ones, but actually the open ones. So that will complete it by itself. Okay? That's it. Okay? This is pretty much it. And yeah, so it will contain the open intervals as well. So if I define another family considering the open intervals on R, and let's say this generates, and this is something which you haven't seen this yet, but the limit of intersection of closed intervals the limit of the intersection of open intervals can be closed. There is going to be an exercise based on that, so I would like you to basically to address this. Okay, so I've done that one. So I'll show you that the limit of a union of closed intervals is not necessarily closed. And there is an exercise basically doing it the other way around. You would need to show that the limit of the intersection of open intervals is not going to be necessarily open. Okay? So that means that if there is going to be a sigma algebra which is generated by the open intervals, okay, that is going to be also containing the closed ones as well. And a sigma algebra that is generated by open intervals, okay, so by this family, right, okay, because that is a family, which is not a sigma algebra, by the way, okay, you can do that quick. I mean, that's what you would have to do, so I will put that as an exercise, and you would need to establish it just the way that I did in the lecture, so you can check that out, you'll see. Okay, I'm going to text you, so maybe you can do it for next week. Okay, this family, okay, is not a sigma algebra, but it can generate one according to theorem 1.2.6. And the family which is generated by open intervals is called the Borel sigma algebra. Okay, over the set of real numbers. So a Borel set is an element of the Borel sigma algebra. So anything that can be expressed by open intervals, closed intervals, their unions, their intersections, their complements, this and that, whatever. Okay, so all the set operators included. Okay, and its elements are called Borel sets, by the way. So this is a very important algebraic structure, okay, which we use basically. Why those? Because, for example, we want to basically establish what's the probability of x, which is supposed to be a random variable taking values between, let's say, b and a or so, right? So within that closed intervals. That's why. Okay, so we need to have those structures basically, and yeah. So, but we need to show them that they exist. And if these basically exist, they also contain the closed sets. Because there is one important statement regarding these Borel sets. Okay, the family that is generated by open intervals on R is identical to the family that is generated, sorry, the sigma algebra that is generated by closed intervals, even if neither the family of open nor the family of closed intervals constitute to be a sigma algebra, by the way. So that is a very important statement, okay? Now, I must say this, but this is just a side note. There is sets which are not Borel sets. So Borel sets are typically open/closed intervals / any union, intersection, difference maybe, complement, whatever created from those intervals are typically the Borel sets, but there are sets on the set of real numbers which are not Borel sets. That's a statement that I will need to, I'll need to address. Okay, so again, that's just very, very technical, and this is going beyond the scope of this course. Okay, so what I'm trying to address is that not every subset of the set of real numbers is a Borel set, by the way. Okay, there is more, much more, but I'm not going to discuss those. If you're interested in this topic, you can Google, for example, the so-called Vitali set. Okay, so but I will not waste some time on that. Just Google it. The Vittel set is not going to be Borel set. It's not even clear whether it exists or not, but that's just an open for discussion. Anyway, so I'm not going to talk about that. It takes time to consider that, but this is just, I don't want to go this far. So we go deep, but not too deep, you see? Okay, so that's not going to be important in this case. Yeah, anyway, all right, guys. So this is something which, again, I want to stress this, okay? So the Borel sigma algebra is not identical to the power set of the set of real numbers. This indicates that there are sets or subsets from the set of real numbers which are not Borel sets, okay? This is a strict subset, by the way. So the Borel sigma algebra, okay, is a strict subset of the power set of the real numbers, okay? But it's not identical to it, okay? So that's something which I want to stress here, okay? So there is sets which are not Borel sets, by the way. That's a statement that I wanted to make here. Okay, guys, the next part is going to be additivity, but I'm going to consider that issue next week. So I will take this off from the slides and I'll put it basically to a new collection of slides. So that's going to be the second part, okay? Next week, we're going to start at 4, and I'm going to talk about measures, in particular probability measures, and further things that relate to basically it. So, for example, measurable functions and random variables. So we're going to define random variables and after all, okay? So that's what we're going to do next week. All right, guys. I hope to see you again. I hope I didn't scare you off. The number of people attending this class has decreased by 30%, is my estimate. But again, I hope it's not going to be that difficult as it appears to be. It's just as always the case, though. Anyway, all right, guys. I wish you a great evening. Take care. That was it. Bye. Thanks.